Welcome everyone to the first fall 2021 seminar in the New Jersey Institute of Data Science Virtual Seminar Series. I'm David Bader and I direct the Institute for Data Science, and I welcome everyone joining here both on this Zoom as well as on our YouTube live stream for today's seminar. We're honored to have Dr. Costas Bekas here. Since December 2019, he's served as the head of quantitative development at Citadel Securities, and he's responsible for large-scale computations and algorithms. Prior to that, Costas was a distinguished researcher and manager at IBM Research in Zurich, and he was responsible for foundational research in AI, spanning areas that include machine learning and deep learning, knowledge extraction and representation, and new computing paradigms for AI, with applications in healthcare and life sciences, materials discovery, and robotics. In 2003 to 2005, Dr. Bekas worked as a postdoctoral associate with Professor Yusuf Saad at the Computer Science and Engineering Department at University of Minnesota. Dr. Bekas's main focus is in cognitive systems and their impact in industry, science, and business. His research agenda spans machine and deep learning, large-scale analytics, high-performance computing, and very large-scale distributed systems. Dr. Bekas is the recipient of the ACM Gordon Bell Prize, actually twice in 2013 and 2015, and the Prace Award in 2012. Today, he'll be speaking on cognitive discovery, accelerating technical research and development with artificial intelligence. Costas?
Well, David, thank you very much. And I would like to thank also Yanis, old colleague from the University of Patras. We go back many years. Thanks a lot for this opportunity to come and virtually meet you guys and talk to your students. Indeed, after a very long career with IBM research. Okay, so I was saying that I decided to move into the super duper exciting world of fintech. Many people will get confused when they see the word securities. They think that Citadel is a company that does software for security and so on and so forth. Basically, securities in the financial world means anything that's tradable. And we mean anything from stock to options to commodities, you name it. Now, the fintech world is an extremely interesting world. And I have to say that while the problems I saw many years with IBM research were extremely interesting, very wide, here we get to see similar type of problems, but I would say much more focused. Now, the key is that the size of the data is really incredible. I would say the quality of the data is always problematic, but the sheer size of the data and the type of decisions one needs to make and the opportunities that are there are just mind-boggling. And they press actually to the extremes all of the capabilities we have at what we call standard computing. And that's what I'm going to try to tell you a story today about where we are with our capabilities in computing today, especially for very large-scale computations, such as the ones that come from extreme data science in all areas. I mean, in the data part, in the compute part, also in kind of, if you will, in the way that we do research, our mentality, and what are some ideas and how AI, I think, can come to the rescue, if you will, and help us move forward. Okay, so usually, I give this slide to describe to especially younger people, to give them a little bit of a reminder that in science we have three pillars. Well, there is the theory, and recently we also call it knowledge. There is experimentation, and theory and experimentation, they are ancient, right? So we don't even know which started first. Was it we theorized what are the stars? Or we started to observe very well the movement of the stars and realized that some were planets and some were stars. So they go back to the beginning of time, right? Theorizing and experimentation. However, in the last, I would say, 50 to 60 years, thanks to the advent of computing, we also have simulation. And simulation in recent years has been of paramount importance. I mean, let's look at it today. Thanks to advances we have in 3D scattering, imaging, and into computing, we got to simulate the protein of the COVID virus, right? That makes us sick. And then we came up to inverse design this protein with wonderful technology in mRNA and others. But simulation had a profound impact in this respect. So these are the three pillars. But notice that in the middle, I put this little typhoon symbol here, right? This tries to symbolize a hurricane, a typhoon. And I want to say that this means that we are going to, or we are already having disruptions in all of these three areas. And let me give you an idea. Last year in material science alone, we had something like 500,000 publications. So who's going to read all of that? And if we put even the patterns, then it becomes enormous. The full idea of humans publishing is done by humans producing content for humans to read. And all of the metadata and all of the wonderful failures that we actually did in order to come out to the successes are lost, which is most of the knowledge actually. So theory and especially knowledge in the form of publications, reports, in general, in the form of unstructured data, is just exploding. Not will explode, it has exploded already. Now, same thing, of course, with experimentation, right? So we do have now machines and sensors that, think of IoT, that bring so much structured data that is simply impossible to just analyze. There's a very famous old anecdote in supercomputing, goes back to the 70s, that says that we have a perfect computer that can simulate the world of tomorrow, the weather of tomorrow, so well in a week. Right? This is where we are right now. We have so much data at our hands that's structured and unstructured, and we have difficulties in connecting it, making sense out of it. But also we have extreme difficulties with the simulation. Let me give you an example. There is this famous list, it's called the top 500 list of the most powerful supercomputers in the world. And right now, we are approaching the so-called exaflop. So 10 to the 18 operations per second. But we're getting slower and slower every year at keeping pace, at bringing these improvements. If you look at the progress between the 90s and the 2000s, the 2000s, 2010s, and the 2010s to the 2020s right now, we are seeing not an exponential slowdown, but a significant slowdown in this respect. I'll explain why. But these three components together, so the difficulties with compute, the extreme amount of data that we're generating, we want to make sense out of it, we want to make money actually out of it. We want to bring value to society out of it. But its sheer size is so big that we have essentially the perfect storm. And we have a major disruption in front of us on the classic way that we're doing technical R&D today. So I'm going to give you this story with a little bit of evidence. Some stories that go back and some things that are even more recent. One example, classic example, in materials science. Believe it or not, material science is one of the most prone or the most research areas that are using large-scale data analysis. You have to consolidate data from experimentation, data from simulations. It's really very, very, very big. 10 years ago, we were working on a problem trying to understand why lithium-air batteries were not actually recharging. So how do you do this? Okay, well, you set up a large-scale simulation, and we did. What you see actually on this side is a simulation. On the y-axis, you see runtime. On the x-axis, you see number of cores, actually. So we went all the way up to 6.3 million cores with this problem. The blue line is the speed up. So the time and the speed up, essentially. So you can see that as we were increasing the resources, the compute resources, we were able to drive the problem from 1 hour per simulation step down to something like half a minute per simulation step. And that advance at compute allowed us to actually set up a very large-scale simulation. We ran on a large-scale blue gene system at the time. Baruch may remember that system in Yorktown. And we actually discovered that one of our team members, a chemist, one of the best in the world right now, Teolaino, who had a hunch that it was nothing with common problems seen before in ion lithium batteries, but it was really the electrolyte that was breaking down, that he was actually right. It was a long shot, but this simulation proved him right. Yeah, it's the electrolyte that breaks down and nothing of the common problems that people have been seeing before with other types of batteries. Okay, and I was younger at the time, and so I naively declared victory. I thought, oh yeah, look, I scaled this code. We found the simulation of the smoking gun. I declared victory. I was so wrong, because victory is when we find the material, the electrolyte, that doesn't break down. Right? That's when you have the battery, not when you find the problem, but when you actually solve the problem. Okay. And then I asked Theo, so how long will it take us to design a new one, right? And he is like, maybe 10, 15 years. And I was devastated. I was really devastated. 10 years to design this thing? But why? And then he explained to me, there's probably 2 million different materials that we could explore. And all of them, they come with an enormous amount of data in unstructured form. You need to read the patents that describe them. You need to read papers that describe them. You need to do data simulation between this knowledge and crystallography data. It's a jungle. And that is like looking for essentially a needle in a haystack. And that's why this traditional way of assuming that compute is going to save us, it doesn't work. So I realized that, oh man, it's not the compute that we scaled that's taking most of the time. It's the actual process of doing research that takes most of the time. It's the reading, it's the getting together of data, it's the cleaning of data. It's all of that takes really the humongous amount of time. So apparently this story, you get to see in other cases. David mentioned that I was fortunate to win the Gordon Bell Prize twice, yes. But this was, apart from wins, these were also very difficult lessons for me to swallow. Let me give you an idea. So conventional wisdom, up until 2013, when we proved it otherwise, would tell you that computational fluid dynamics is a thing that scales. You can put it to hundreds of thousands of cores, but you will not get a big chunk of performance of the machine. Basically, you get 2% of the machine, 3% of the machine. So the remaining 97% of the expensive GPUs or whatever you're putting there fails. So I partnered up with a bunch of guys from ETH and Munich and Lawrence Livermore, and we really did a tour de force. I was locked in my office with a bunch of guys working like crazy, 10 months. And we went through about 2,000 papers that were dealing with sparse matrix vector multiplication. Why? This is the most important kernel for these things. Apparently, sparse matvec is everywhere, but it was the thing that we needed to scale. Now, the literature on this, it's just phenomenal on one side. On the other side, the literature on the blue gene system itself, the processor design, right, that was even more cryptic, and it's very complicated. So then I realized again that this type of compute that we were able to achieve, it's kind of a one-shot thing. You need a super duper team of the top experts in the world and a lot of luck. It's not repeatable. And the enemy, again, is the complexity of software, the complexity of data analysis. It's the literature that's enormous. So again, the same story painted in front of my eyes. This was, in other cases as well, here I partnered up with Omar Katas from Texas, but there were also geologists involved. And there I was like, this is the last straw. You know, now we needed to understand also in the disciplinary stuff, right? You have the math, you had geology, this is about Earth simulations. And that paints the other part of modern science, which is if you believe that you're going to have an impact, a true impact in society, only in one piece of science or technology, that's not the case. The impact comes when you bring a lot of stuff together, different stuff together. And then you have, again, the problems of data in different formats, data in different language, in different in scientific language, in different domains. The conventional way of working, even though you can be successful, cannot trickle down and become standard practice everywhere, which will hopefully bring exponential increase in impact to society. Okay, so these are lessons. These were lessons that I learned through success, but a very hard way. So around 2015, I started to come up with this realization that we have to do something. Now, I also told you before that we have an issue with simulation, especially with machines. So let me spend a couple of minutes to tell you a little bit of the story there. Okay, so this is Moore's law. Basically, Moore's law tells you, and I deliberately stopped at around 5 years ago, but Moore's law tells you that more or less, we kind of double the number of transistors in the same area in a chip every 18 months. It is actually a factor of 1.4 every 18 months. And this is the plot, and it's a log-log plot, more or less, and you can see it's a great straight line, right? But notice something. If you look at the machines around here, and if you plot the machines today, which would be around here, the progress in the number of transistors continued. So now we have chips with 24, 48 cores. We have GPUs with an enormous amount of multi-chiplets and many cores. So that went on. However, Moore's law is not about speed. It's perceived to be about speed of computing, but it's not. It was never about speed of computing. Physical principles meant that it was about computing, and let me explain why. Now, if you make transistors smaller, what happens is that you can drive them with lesser voltage. If you drive a transistor with a smaller voltage, then you can flip it in faster. There is an inverse relationship, square actually, between the voltage that you drive a transistor and its frequency that you can run it. And guess what? Already 15 years ago, we plateaued. The best processor you can buy right now is about 4-point-something gigahertz. You will pay an enormous amount of money for that. IBM just announced about 10, about 5. But we also had the mainframe chip many years back around 5 gigahertz. Today, we should have been more than 20. We are not there by far. We are not there. So what happened? As we make them smaller, the transistors, we have to run at lower voltage. At some point, when the voltage becomes too small, they stop being the transistor. They stop being a switch. You have leakage. Basically, quantum phenomena start to appear, such as quantum tunneling, and you have electrons that jump through the barrier. So you have leakage and increased temperature, and even more leakage because of the increased temperature. So really, that's the reason why we cannot drive them faster. And that's the main reason why Moore's law is not about speed. It used to be for decades, but since 15 years now, it's not about speed, or at least not about automatic or lazy speed. So what did we do instead? Well, instead, we became multi-core. And that's what you see in this plot. Again, this finishes about 10 years ago. So what you see here is the following. This plot I worked together with my friend and colleague Petros Koumoutsakos from Harvard. He used to be at ETH. Basically, what you see is the top 500. You see historically, this is the green line, the top systems. Then you see actually the top 5 average. Then you see the power requirements. But most importantly, what you see is so-called efficiency gap. So what people do in many data centers and HPC centers is the following. They say, what percentage of peak performance is the average application achieving on our systems? And you will see that since 15 years back, since we start to make complicated things and frequency scaling stopped, we have an increasing productivity gap, an efficiency gap, meaning that we can run more and more and more applications on a big machine, but we cannot run an application very close to peak efficiency. This has been one of the main driving factors of abandoning on-prem computing and going to cloud computing again. So remember, cloud computing, I say again, because cloud computing, it's not a new notion. If you go back to the first mainframes in the 60s, you will see that they were the first cloud systems, basically a system that you share with many people and you have some sort of time sharing, virtual sharing, and you pay as you go. So the main issue is that why should I invest in all of this expensive hardware where my efficiency gap grows? So, and that is for average applications. When you go to the extreme, it's even more pronounced. But let's focus on data science for a minute. I have a habit of asking always the team that I'm working with since many years now. We do a benchmark of the latest model in deep learning, take either a visual model like Inception or whatever else. And since 2010, I keep a track of the performance, the peak performance the models achieve on the GPUs. And when you go back to 2013, AlexNet at these times, you would see that we were close to 85 to 90% of utilization. And today we are less than 30%. So basically, 70% of these tens of thousands of dollars that we pay for these systems, we throw away. We're not using them. So the message is, we cannot expect that somehow compute magically is going to solve our problems. It doesn't by just waiting that it will become faster. So we went into a complex world recently. We start to see the merging of traditional high-performance applications with applications that in the past were considered to be more of data-driven. For instance, querying DBs and information retrieval. They are data-intensive, they need huge volumes of data, but they are low in complexity. So you can deal with that with large-scale data science systems, with your MapReduce and so on and so forth. However, recently we start to see more and more sophisticated compute-hungry algorithms being used in data science. Deep learning is one of them. There's also others, meaning that they start to cross into the high-performance computing world. And in the past, this little niche that was HPC was very happy with its whole world, getting their money from DOE in the US and from the European Commission here in Europe. But now it starts to be the element of large-scale data science. Okay, so this pays even a more complicated domain here. And I think I promised to you that I will show you how the publications are increasing. And here's, I keep my word. This I'm going to stop the introduction essentially of the problem with this plot. So what you see here is historically, starting in the 80s, the number of scientific publications in just material science alone. It's incredible. Okay, it's just mind-boggling how it has increased. Okay. So what's wrong with the way that we are doing things? Let's see this. Now that I painted the problems, if you will. Well, mostly we're using this type of, I call that the Edisonian approach. Basically, we start with some ideas we have in our heads, some hunches, discussions we have with our colleagues. COVID did not help that much with that. But there are so many things that you can discuss with your colleagues at coffee, and you can come up with ideas, and you can get a hunch, right? But all this needs to fit into this little Kean triangle here. We are creatures that we have problems communicating with more than 70 or 80 people concurrently. And this is even so in social networks. You will see that we have thousands and thousands of connections on LinkedIn or wherever else, but we are rarely communicating directly with everybody. We have still a smaller amount of people that we speak to normally or regularly. Smaller one. There's this very nice book of Harari that explains a lot of stuff in this direction. I recommend to the younger guys to read Sapiens. It's really very nice. Now, so what do, right? We take our ideas and then we go out and we use machines experimentation and we find out, we create a universe of possible solutions. Like Edison, try and try and try and try and try. Of course, every now and then there will be some genius like Tesla who is able to go directly to the truth, right? But these are very rare cases. Let's put it this way. So the standard approach we follow in science, as we have to admit it, is this one. So now, if we have to fit 1 million papers a year in this little triangle here, it would not work anymore, right? So basically, this window to the full world is so narrow now that it's simply impossible to use standard practices, standard way. Like, remember my advisor, Stratis Galopoulos, David, you may remember Stratis, was telling me, Costas, every week you will go to the library back in Patras in Greece, and you will read the latest in the Siam journals. And I was like, I want to tell him, Stratis, you're crazy. We have everything electronic now. Of course, I fully respect him. I could not say anything like that, right? But I told him, have you seen that we have everything electronic now? I don't need to go to the library. 3 years ago, I graduated before I went to the fintech business. I graduated my last PhD student back in IBM Research. And if I was to ask Roxana, who now works with Google, to go and read everything every week on auto-tuning for deep learning, she would tell me, Costas, you are completely crazy. There's so many papers that every week that come out, there is no way. And she was right, okay? So it's a problem there. Now, with simulation, you see that we are now already at our limits. So this is, I believe this is the way that we're doing science, is actually the bottleneck here. So we have issues with knowledge, issues with evidence, issues with simulation. Let's try to reimagine it a little bit and try to use some of the most recent advances in data to our advantage. For instance, what if we develop technology using the latest NLP, natural language processing, that is able to read automatically all of these millions of papers, extract, for instance, the numerical formulas, extract the tables, extract the diagrams, invert actually this data and organize it in a way that is searchable, even searchable with concepts, right, beyond the simple keyword matching. So imagine I want to ask a question. Here's a formula for a new reaction, chemical reaction, Okay? Did anybody publish anything like this? Today, it takes us months. There is an estimation that the average chemical engineer in Europe spends about 3 hours a day searching on Google search. Okay? Now that we actually did back in IBM a professional study for this, and that's completely true. Now, what if we use, however, all of this computer vision, NLP technology we have, and the advances in databases and data simulation to actually organize the unstructured knowledge into structured knowledge? And what if we use graph analytics to try to go into, and I'll show you some examples, to try to go into hypothesis discovery, to try to go into automatic null hypothesis analysis, to try to actually make sense of humongous amount of data. So instead of starting from a narrow base, start from a huge base that we extract from everything that we have at our disposal, put the human at the center, so human in the loop. Of course, human guides stuff, right? Instead of all of the possible simulations you can simulate or surrogate the majority of them with data-driven models. I'll show you some advances, incredible advances we have now in using deep learning and other technologies in predicting simulation outcomes. In most cases, a simulation would be useless, something interesting. Useless, something interesting. If we could screen 99% of the useless just by doing data analysis, we save 99% of all of the cost of simulations. So we can really use the remaining cycles in the best possible way. For instance, then you can design the simulations you are doing in such a way using powerful techniques that are now possible, such as Bayesian inference, Bayesian optimization, that can do simulation driving and design of the space and so on and so forth. So the idea is, instead of going classic Edisonian and expanding, admitting that we are not Tesla to have the brilliant insight immediately, try to capitalize, as Bismarck said, from the mistakes and from the knowledge of everybody else. And use the AI technology to come down, to narrow down, and only at the end do the expensive experiments, the expensive simulations, and thus maximize the chances that we can achieve something. This is really the crux of the message that I want to pass to you guys today. If you remember something from this message from me, that's it really, that we do have now the data quantity. And finally, we have enough compute to do this. We don't have enough compute to continue the old way, but we have just enough compute now to actually do the other way, the way of the inference, the way of going focused instead of just mindlessly expanding. Okay. Now I'm going to show you a bunch of examples in all of these three areas, like extraction, surrogate modeling, but I'm also going to spend some time to show you some of the most exotic things that are out there for compute that I'm also considering. And I have worked into, but I'm also considering for the next phase of compute. So I never said that we will abandon compute, right? Because the better compute we have, the faster discovery is coming. Okay. So here's the full map, the full pyramid of technology essentially that we need. At the bottom, we need knowledge extraction and representation technologies. Knowledge extraction from any piece of information. I put here the biggest enemy, which is PDF, because this is everywhere. We use it everywhere, and it's the worst in terms of metadata. Doesn't keep anything. Basically, it's instructions of how to print ink on paper. Okay, all the way up to inference-driven simulations, right? Natural language querying, machine-driven simulations, domain-specific machine learning, and inference. I don't believe that we will ever have something like general-purpose intelligence, as we don't have, since Poincaré is dead for 100 years now, a general-purpose or a general-purpose scientist that can do everything. We don't. Poincaré is dead 1910, right? That was the last guy. So this means that as we are educating our children in a specific way, in specialties, we will have to do the same thing with inference and with AI, with machine learning. That I believe firmly in that. Maybe I'm wrong, but that's what my experience has shown. Then we need to go towards hypothesis discovery, which is the biggest problem. That's where we spend most of our time as humans. So if we do technology to help us there, this will be great. We may never reach fully automated discovery or fully automated reasoning, but we have to have a target, right? So let's put the target high in this respect. Now, let me show you first example. So, as I said, for science, for instance, documents in PDF is everywhere. Unfortunately, you would think that we have LaTeX sources and metadata, but that's not the case. Really, what survives out there is mostly PDF. But even if you had metadata, the data you use, the technology you use to create an image in the metadata or a table in the metadata is not there. This is lost. By the time you give it to the world, it's lost. So the idea was to develop a technology that would work like a human, like take a page and first understand its structure, like what part of the page is a formula, what part is a table, what part is a diagram. If you are in a diagram, what is the x-axis, what's the y-axis, what are the lines, can you invert that back into a table? Okay, if you are in a table, what are the headers of the columns, of the rows, so you can ask queries on these things. So today there is a lot of conferences, finally, that will deal with this. There's competitions to understand tables and so on and so forth. It's becoming a very, very, very cool mainstream thing. Finally, I was advocating that for years, but now it's really starting to be mainstream. So I many years back, 5 years back, actually, I sat down and I told my team, enough with gold Nobel prizes. Now we're going to do this. We're going to invert PDF. And they were like, you're crazy. No, we're going to invert PDF. So for that, we did a very large scale system. Now it's a proprietary IBM product in Watson Discovery that is being used everywhere, not only for scientific applications. Now imagine you may have credit card reports. If you're an insurance company, you may have accident forms, you may have doctor forms, anything. People believe that they are done when they scan them and they put them somewhere. No, you're not done. You need to be able to index it and ask questions and do statistics on that, right? So this technology utilizes a cascade of technologies. We published that in KDD first time, 2018. It uses a combination of hierarchical random forests, novel classifiers, and then we also did a technology that you can combine features that come out from random forests with deep learning, random standard models. So the idea is that a random forest, you can teach it with a small amount of data. So you let people annotate graphically like what you see in the third picture here. So they annotate graphically, they paint blue the abstract, or they paint with their mouse, very easy to use, this yellowish color, the text and the formulas and the authors, okay? And you do that for a few pages, but there is also a base deep learning model trained on enormous amount of corpuses from LaTeX sources and whatever we could put our hands on, okay? Also utilizing about 200 200 annotators back in India and China and in every place, annotating thousands and thousands of pages, right? But then also the interesting technological part and the scientific part was how to merge these two models, the deep learning world and the hierarchical random forest world. And we have a bunch of explanations in KDD. That was interesting. But bottom line, you go from this guy into JSON, annotated essentially all of the structures. Now, another example I want to show you. Now we move from extraction. So let's say extraction tick, not really tick, but we have now some technology, right? Good. And there's also many other technologies out there. Now let me show you examples how we can surrogate simulation. So 4 years back, we were discussing with again my friend the chemist Theo Laino if we could teach deep learning how to learn organic chemistry. That was a joke in the cafeteria. But I was thinking, I remember school, I was able to learn chemical reactions not by heart, but because it looked like a language to me. Okay, so if it is a language and you have components that react and you have components that are the outputs, is it not too crazy to see this like a translation? Like translate the input language to the output language, like translate English to Deutsch, like English to German? It worked like a charm. So we only used in the beginning sequence models, basically the same model that Google used to do the translation with very minor changes, okay, very minor changes. Then in the meantime, we came up with completely new transformer models to do it. But the bottom line is that we came up with this technology that's called RxN, so reaction. You can look it up, you can play with it, it's free on the web. If we have time later, I can show you a little bit, but it's easy. We sold that to the American Chemical Society annual meeting in Boston, like in August 2008. And we organized competitions. 240 teams formed, professors, students, friends, you know, they tried to beat the system and they lost 2080 in time. The system was always correct. But sometimes it would also take some time because humans had the result immediately. Okay, so that this system we trained with something like 10 million examples of organic chemistry, and the trick is you take the images and you translate them into a text representation that's called SMILES, canonical representation. So basically, it's a text-to-text translation in this respect. And the first results came out cross-validated 92% out of sample accuracy. This is incredible. At the same time, however, the system was failing in some very simple textbook reactions that every first year chemical engineering student knows. Okay, why? Well, people don't put simple chemistry reactions in databases of reactions. They put extremely difficult stuff. Okay, there they only put kind of they don't put the easiest things. This is where the extraction from documents come in, and now there is a complete system there that's very, very accurate. And my old colleagues at IBM, what they did now is that they also closed the circle. So when a reaction is interesting with high confidence, as the system says, they actually send it to a robotic reactor, and they actually do it, they measure it, and they verify it. So this is a complete circle. So now there is a bunch of companies and a bunch of big startups with huge evaluation all around the world that believe that this is the way that drug discovery is coming into the future. Okay, and there is already a few things that came there. Okay, a little bit now about the math. Okay, the third element of this. Now there is, in my opinion, there's many ways to formulate analysis of knowledge. My favorite one was always working with knowledge graphs, with graph information. So a knowledge graph is nothing but a super duper hierarchical, multi-dimensional graph where you have types of relationships in many kind of levels. You can see it as a multitude of simple undirected graphs if you wish. In the end, you can completely unfold it like that. Okay. So the answers, the hypothesis was that graph properties and graph analytics have a lot to tell us about the knowledge. Inspired by the success of graph algorithms for internet search, we aspire to use graph analytics for knowledge analysis. But unlike PageRank, that is shallow, that looks only at the dominant eigenvector of the matrix, it was clear that we have to go to more sophisticated technologies such as subgram node centralities, in between the centralities. We had to go to spectral centralities and a lot of things like that. Now, these are very powerful. People know them. The problem was that you needed an eigenvalue decomposition of the adjacency matrix. That is a no-go. It has cubic complexity. If you have a graph of size 1 million, that's an exascale already. If you go to normal, the knowledge graph we have for the organic chemistry, for instance, is already 500 million, so bye-bye. There's no way. So for many years, actually starting working with SAD back many years for electronic structure theory, there's actually connections there. Density matrices and graphs, knowledge graphs, they have strong connections. I realized that the problem can be formalized by computing some elements of a matrix function. So, for instance, PageRank is just a quadratic function evaluation. A subgram node centralities, which is this guy, is actually computing the diagonal of the matrix exponential. So it turns out that you can write almost every important analysis algorithm or metric for machine learning as some matrix function, out of which either this is going to be a sparse one, so you're only looking for a few elements, or you're looking for a few elements of that matrix function, like the diagonal or the trace. The trace is the simplest thing in this case. So I really developed, for working many years, I developed a framework with my teams over the years that actually is using stochastic matrix function estimation. This work started with SAT back in the mid of 2000s. So the idea is, how can I, using only a matrix vector multiplication, so I have the matrix, I don't have the matrix function, but the matrix function times a vector is something that I can do. That's the assumption. Like in the radar, for instance, we don't have e to the a, but we need e to the a times a vector. That's the solution of the PDE to retrieve the signal in radar, for instance. So e to the a times a vector, anybody in iterative methods will tell you, oh, that's a Langström's method. We can do it. Now, on top of that, I know that I need to estimate matrix functions that are sparse. So how do I do that? So there is a full theory working for many years with several teams. Baruch may remember the sketching project, maybe also John, we had back in IBM and with colleagues from the West. It was a DARPA project. So there is technologies like sketching, sampling, stochastic estimation, matrix expansion analysis. Here I'm mostly using actually Chebyshev analysis of matrix functions. So a Chebyshev polynomial times a vector, again, is something that we can compute. I'm not going into many details, but the bottom line is that you can estimate matrix functions if you only need very few elements. And if you only need a few digits, you can do that efficiently very fast. And remember, we are not looking for 60 digits. We are only looking for orders. We're looking for how to order things in the search. We don't need 60 digits of accuracy to do PageRank, for instance. We don't really. Okay, so you can take that into advantage, and you can come up with some results. Now, there is many details, but what I want to end up with is a couple of minutes on where do I see the technology on the hardware moving forward. And I'll start with let's say with a disclosure. Quantum is difficult. It has great promise, but I personally don't believe that it's going to ever be a universal technology. It's going to be a super accelerator. So I like to think of that in this manner. So think of, we have on one side some sort of reliable, classic type of computing where we can tell it exactly what to do, where it's easy to load data. And on the other side, we have some noisy, not always reliable, but extremely fast. And actually, the notion of data movement does not exist even in this respect. Okay, but there are inaccuracies. So how can we do computer architectures that combine these guys to come up with exact results? Well, it turns out that at least for a large scale of problems like solving linear systems of equations, for instance, you can go back to the well-known techniques such as iterative refinement, where you can do the bulk of your compute in very low precision, a little bit of correction in high precision, like 0.1% of your compute in high precision. You combine the results and you get fully accurate results. That's what you see here is computing the inverse of a covariance, like we are computing the inverse, the diagonal of a precision matrix. It's very important thing if you want to do data assertive quantification. And what I showed you down here is the numbers to realize is like the energy goes from 103 kilojoule to 0.3 kilojoule. That's what we are gaining. And the time actually goes from 546 seconds down to 1.8 seconds. That's what you can use. Of course, if you stick with conventional way of understanding things, which is, oh, I only measure flops per watt, that's not very good in that metric. But ask yourself, am I asking the right question? Do I have the right metric today for the problems that are important now? If compute is really coming to an end in the classic way, why do I care about flops anymore? We have to think out of the box again, okay? Last, I want to finish with a few ideas on what I believe is intermediate to come before quantum will become mature, which is so-called in-memory computing. And I'm going to give you a graphic like that. So now we have so-called phase change memory technology. Basically, we have materials which that they can remember how many pulses have went through them. Okay, I can remember how many pulses. So what's that? That's like a counter, right? Okay, so we have machines that can be a counter there. And we also have machines that we can combine them in a way. I think I had somewhere, yeah, there. And it turns out that if you arrange them in the proper Kirchhoff circuit, you can route these pulses so that they also become additive. So I have a counter and I have an adder. I can't do anything, right? With a counter and an adder, you can really program anything. We know that, it's proven. So basically, okay, here we just do a matrix vector multiplication. If I do matrix vector multiplication, I can write down my iterative refinement. Basically, I can write down a conjugate gradient method, okay? So now imagine we have this big chip that has phase change memory. You load it with all the data and you just supply it with pulses that emulate the input, and it does all of the arithmetic without data moving at all. So you just read the data on the output. Theoretically, and this has been also, I mean, we published that in Nature, and there's another paper on Nature that shows that if you do the inverse, you can get the inverse of a linear system this way, even. Not very accurate. Maybe a digit and a half, maybe in the best case, there is thermal drift. But if you combine that part with some accurate computing that will work periodically on that residual, you end up with this type of plot here, which is 6 orders of magnitude improvement in your residual. That's what you do in iterative methods. You declare victory. You solve your system. Okay. So, all in all, yes, if we continue in the way that we are working, we are with our backs on the wall, I think. But we have enough advances done that if we change it around and if we use AI to understand the knowledge, to organize it, if we use inference to substitute most of the simulations, if you use Bayesian optimization to guide the simulations. And if we, thanks to all of these advances, believe and just embrace new types of hardware like the quantum or intermediate like in-memory computing and approximate, and really ask the question, do I really need 16 digits? Okay, we have still, I believe, an exponential capability to do impact. So thanks a lot. I took more time, I think, but thanks a lot for listening.
Thank you, Costas. That's a great talk and very, very thought-provoking. And if there are audience members with questions, please put them in the chat. A few questions came in, so we have time to get to a couple of them. The first, appreciate the talk and anecdotes, Costas. On the practical side, would you mind sharing your thoughts on the progression of open source parallelization frameworks, and specifically what components of such frameworks you feel will persist? For example, if one considers the progression we have seen over the last decade from Hadoop to Spark, BigQuery, Redshift, to now more cutting-edge specialized tools such as those you build like Tor, CPY, Lib, Skylark, what features common to all such frameworks do you find would be the most useful, and what are you trying to improve or replace?
Yes, that's a very good question. Actually, I worked on that question exactly 3 or 4 years back. We were writing, I was the author of a chapter for the European Union about the convergence of large-scale data science programming technologies with HPC technologies. So you will see what happens is that we move from the bottom, or we can even reverse it if you like it. But let's say from one side, we have the big data world that in the beginning developed technologies that were grid-like, so mostly for resilience, redundancy, because disks failed and this and that. But then they went into more of in-memory compute, and they realized, oh, it doesn't fail so often, right? And on the other extreme, we had systems that were on for supercomputers that didn't really fail because they were very much engineered. So for instance, message passing interface and CUDA and this and that. And what we start to see is their convergence in this respect. And so that's really very interesting. So here's what I think, however. Parallel computing is not easy. It's difficult. Automation in parallel computing is not there. We have been trying since the late 90s. We came up first with OpenMP. OpenMP now is still the best for general purpose parallel computing for threaded computing. But still, if you don't pay attention and if you don't know what you're doing, you don't get the performance. So yes, it's easy to get set up and get something, but you don't get performance. So let me give you 2 examples. One example, if you want to run very large scale, let's say clustering with MapReduce, good luck. It's okay when you have millions of data samples, maybe, but when you have billions, it takes forever in this respect. On the other side, similar technologies for molecular dynamics, they utilize point-to-point communication, efficient communication like the stuff that came out from DSO research on Anton, that is order 1 communication, regardless of how the processor count increases. So that's what we need. We need these 2 worlds to merge, but we also need a lot of education for the new generation to realize that there is not going to be a free lunch. Parallel computing is difficult. This is why, for instance, if suddenly somebody would come with a processor that runs at 100 gigahertz, most of the people would abandon parallel computing immediately, okay? Because it would be just easy. So there is no free lunch with parallel computing. Basically, we substitute an exponential increasing technology like CMOS with this now. We have to think of how to parallelize algorithms. So my suggestion to the younger people, but also to the practitioners and to the professors, as I see it from my field, that now I work with petabytes of data every day, every single day, okay? Hundreds of petabytes of data, if you think about it. So automatic tools and standard big science tools don't cut it. We need HPC kind of thinking, which means educate yourself in algorithms. Don't imagine that automatic tools are going to work for you. They fail in practice. And learn extremely well the basics of linear algebra and parallel computing. Now, at the productivity, at the companies and the open source technology already know that, and they already start to merge these two worlds. So that's happening now.
That's really fantastic advice for our students. I really like to hear that, and a lot about getting people to think about their problems and how to design the new algorithms, and also foundational concepts, I think are very important. There's a very interesting question from John Gunnels. You're talking about publishing and this rate of publication. And his question is as follows: does the publishing of negative results become more important, for instance, have higher utility as you approach the reality of, quote, flipping the funnel?
Absolutely. And I think maybe some time ago we discussed with John this, but so a classic question that comes is, you are forgetting all of the silent evidence, right?
Yep.
If you only look at published things, you are forgetting the silent evidence, the cemetery of ideas, right? You don't see this. That's true. It's completely true. This is where graph analytics, for instance, it's very important, and technologies to actually tell you where are holes in the data, where are holes in the knowledge graph. So the white spaces, something that should have been there, but it's not there. Okay, so that's an interesting part. So this is why I believe that every organization, university, but especially companies, they need to build a corporate mentality that no piece of data is left to die. Everything should be captured and properly, if you will, analyzed, especially the one that failed.
So I was pleased to see your discussion of petascale computing and your fantastic results, especially on the Gordon Bell prizes. As you know, we're at the cusp of exascale computing with
Yes.
countries like the United States, China, Japan, Europe, all vying for having an exascale computer that can do 10 to the 18th floating point operations per second using megawatts of power. Do you have any thoughts about all of the diversity of chips and manufacturers, or what that means for a high-end programmer going forward? How are we going to deal with all of these different types of architectures?
It is an exciting area to be in this business now, an exciting era. So if you were to go, for instance, back in the late 90s, maybe middle of 2000s, it was also so dull. There was basically no interesting architectures out there. But now, as we have, we are with our backs on the wall because of Moore's law essentially drying up, we have all of these new technologies. I personally work with several companies in innovative companies around the world. We are very much interested, and especially that's why Ken is a big supporter of a company of academia and all of this. And we really believe that we need this diversity of ideas. Now, this comes with a cost, of course, right? And the cost comes. The cost is so much more information. For instance, I have seen there is a startup that's now more than $1 billion, $1.5 billion of funding. That's in hardware startup for pros. That's unprecedented. Okay, and if you look at their architecture, looks like a systolic array. So if you are older, or if you liked computer history back in the late 80s, you will say, oh, wait a minute, I remember that. That's like a systolic array. But of course, with many, many, many modern twists. And if you look at other architectures,
I studied that in school.
You see, and then if you look to other architectures, you will see things like very different, right? So there is a huge diversity. We are right now at the funnel out for architectures, which is a good thing because there's many ideas that are people trying, and there is VC capital is abundant, and governments are also giving a lot of money. So our students should not be, and our people should not be afraid. These are only opportunities. Now, the basic principles, they are the same. Data locality, complexity, knowledge representation, trading compute with accuracy, data movement, this stuff don't change. They're the same. So learning the fundamentals, the principles well, will always pay out. Now, will all of these architectures survive? Well, it's very difficult to do projections, especially when they're about the future. But if we go to the past, if you look at early 2000s and early 90s, and actually there's a great book by David Cook on this, there were at least 6 different super-duper HPC supercomputer companies out there, like Kendall Square, like thinking machines.
Yeah.
Right? And they all went belly up in that respect. So maybe something like that happens now. I doubt it, because unless we have some sort of a fundamental physical principle coming up and making things again the same, right? Because it's that simple, big fundamental principle, like it was CMOS, that just drove innovation in one direction, then there is so much more opportunity on the architecture rather than on the physical principle, right? And even at quantum computing, if you look at quantum computing, you will see there's at least 5 different ideas for qubits today, even photonics. So I personally like it, and I think it's a great era for students to come out now, and for young scientists to come out now, because even if they spend 5 or 10 years on something that may die in the end, they would have learned so much in the meantime that it's going to be the perfect foundation for a great career.
So I'm sorry that we won't be able to get to all the questions. We have to wrap up the seminar now, but I want to thank all of the audience who has attended, to you, Costas, for this great talk and this wonderful conversation. So thank you again for speaking today.
It was a pleasure. I'd like to thank Yanis and you for inviting me. And hopefully next time I can see you guys in New Jersey.
You're always welcome.
Let it be soon.
Let it be soon. Okay.
Yes, okay.
When we Schengen people are allowed to come to the US, we will come.
And vice versa, I guess.
You guys can come to Europe. We cannot come there.
I know something changed recently. But
okay. It did? Okay, I'm coming.
Something's going on. But yeah, okay.
Okay. Thank you very much, everyone. Have a great day there.
Thank you. Take care.
Bye-bye.
Thank you.